Lesson 13, Inverse Trigonometric Functions Continued. In this lesson, we are going to continue from where we left off in the previous, where we had talked about the inverse functions for sine and cosine, known as arc sine and arc cosine. In this section, we're specifically going to be talking about the inverse functions for arc cosecant and arc secant, and we will talk about the other two functions, arc tangent and arc cotangent, in a separate video. Here, first, again, we're going to be talking about arc cosecant, which is going to be the inverse function for cosecant that allows us to take a ratio of sides and find a particular angle measure. Now, just like with arc sine, the angle measures that arc cosecant can result in are very particular. If we look at the original function for cosecant, which I have in the bottom corner of the screen here, cosecant is a periodic function. Therefore, it would fail the horizontal line test because it hits multiple times on one horizontal line for that function. Therefore, the entire full inverse would actually not itself be a function. So, just like with arc sine and arc cosine, we only need to take a portion of it. And we want to take a specific portion of it that, one, will pass the horizontal line test, and two, is as similar to arc sine as possible. And what I mean by that is when we look at arc sine, the portion that we designed and used to find arc sine was from negative pi halves to pi halves for sine. We chose that because after both of those points, the curve would start to curve either down or back up, and therefore start to fail the horizontal line test. But from negative pi halves to pi halves inclusive, everything was fine. So we're going to try to use something as similar as possible, and we should be able to use from negative pi halves to pi halves. Negative pi halves to pi halves on this curve, if I draw that in blue or black, would look just like this portion of the curve. So it would not include any point where it would start to curve back in, and therefore would not fail the horizontal line test. However, there's going to be something unique about this, and that is that we're going to have an asymptote right through the middle of this function. This is why, if you look at the graph for arc cosecant that's already included here, we have an asymptote that originally was on the y-axis, is now on the x-axis. And we have these curves that approach the asymptote. They approach the asymptote in the negative direction, approaching negative infinity, and then towards the positive direction, approaching positive infinity, with a big gap of values right in the middle here. This, however, should not be too surprising, because remember, for inverse functions, what you are inputting, the x value, are ratios of sides. We cannot have a ratio of sides that's between negative 1 and 1 for arc cosecant, because that would imply that the hypotenuse side is smaller than the opposite side. We have to have something with ratios larger than 1, or less than negative 1 technically. That would imply that the hypotenuse side is larger than the opposite. This is why the domain for arc cosecant ends up being negative infinity to negative 1, where negative 1 is inclusive, as well as 1 to infinity, where 1 is inclusive. Note that this is the exact same domain, or this is the exact same set of values as the range for cosecant. That still holds true as it does for every of the trig functions. The range for sine ended up being the domain for arc sine. Same is true here. The range, however, just like with arc sine, the range for arc cosecant is not going to be the same as the domain for cosecant. The domain for cosecant was all real values except for where you would have an asymptote, which would end up at any instances of pi times k. For our range here, we are more restricted. Looking at my graph, we don't go any higher than pi halves, or we don't go any lower than negative pi halves. And we also have an asymptote in the middle. That means our range would therefore be from negative pi halves up to that asymptote of 0, not including 0, And then from 0, again non-inclusive, to pi halves. This is very similar to sine, or arcsine, which has a range of negative pi halves to pi halves. This is the same range, but with 0 cut out. The symmetry for arc cosecant is also going to be the same as the symmetry for arcsine, which, as you may remember, is odd. That means if you have a negative input for arc cosecant, you can rewrite that as negative arc cosecant with that positive input. Some other piece of information that we have here regarding cosecant and arc cosecant. If you take cosecant of arc cosecant, that will cancel out those functions and results in just the value on the inside of x, so long as x is greater than or equal to 1, or the absolute value of x is greater than or equal to 1. This, again, is basically just saying that cosecant of arc cosecant will cancel out so long as x actually defines a realistic ratio for hypotenuse over opposite. If x was less than 1, then that would again imply the hypotenuse is smaller than the opposite, which cannot happen in a right triangle. The second line is a little bit more concerning here. When you do arc cosecant of cosecant, as discussed in the previous lesson, you need to be very careful when you could do this. They don't always cancel out and give you x, but they will, so long as that angle measure inside of cosecant is between negative pi halves and 0, or between 0 and pi halves. Basically, so long as that value of x is inside the range for arc cosecant, then yes, you will just get that value back in return. But say if this was arc cosecant of, I don't know, 3 pi fourths. 3 pi fourths would be too far outside of that range. So when you do arc cosecant of 3 pi fourths, that will not just cancel out those terms and give you 3 pi fourths. Instead, work from the inside out to get arc cosecant of 3 pi fourths, which is positive square root of 2. And then take arc cosecant of positive square root of 2, which, because it is a positive ratio, must give you an angle measure between 0 and pi halves, because that is where cosecant is positive. And what you'll get here is pi over 4 instead. So be very careful about those functions. The last note that we have here, which is an additional note than what we had in the previous properties for arc sine and arc cosine. Because arc cosecant is not a very common function that, if you want to approximate, that you can use a calculator for. So we need to know how to change it back into arc sine. Thankfully, it's relatively simple. Keep in mind that sine and cosecant are considered reciprocal functions. This is because they define reciprocal ratios. Sine is opposite over hypotenuse, whereas cosecant is hypotenuse over opposite. What flips between them is that ratio. And when you're talking about inverse functions, the ratio is not the output of the function, it is the input. So when you're trying to convert from arc cosecant to arc sine, you don't flip the output and have 1 over arc sine or something. You are going to flip and take the reciprocal of the input, because what you put into an inverse function is a ratio of sides. So, for example, if you wanted to do arc cosecant of, let's say, 5 over 3. If you wanted to approximate that using a calculator, you would instead do arc sine of 3 over 5. Using this actually demonstrates that many times individuals will actually evaluate functions of arc cosecant by changing it into arc sine instead, which is a common strategy that you can absolutely apply if you would like. Let's move on into arc secant. Arc secant is going to work in a very similar fashion as arc cosecant. That even holds true for trying to find what portion of secant we want to use to find an inverse. For arc cosecant, we had referred back to arc sine and considered looking at the range from negative pi halves to pi halves. The same will be true for arc secant. We will refer back to arc cosine this time. And when we graphed arc cosine, we actually used the range from 0 to pi, because from that range, we did not fail the horizontal line test. That is also true for arc secant. We can see secant here in the bottom left corner. And if I draw from 0 to pi, that would include this portion of the curve that I'm shading in black. The part of the u that goes up there from 0 to pi halves, and then from pi back to pi halves that goes down. As well as, yet again, an asymptote right through the middle. This is where the graph for arc secant comes from, where it goes from 0 up to pi in the y direction. There's a big gap in x from -1 to 1, and then from both values of pi and 0, we have these curves that approach the asymptote both towards positive and negative infinities, but never touch the asymptote or cross it. So, our domain. The domain for arc secant, just like all the other inverse functions up to this point, is the exact same thing as the range for the original function. The range for secant was negative infinity to -1 with 1 to infinity. The same is true for arc secant. The domain for arc secant is negative infinity to -1 union 1 to positive infinity. Note that -1 and 1 are both inclusive. The range, on the other hand, the range is going to be that section of the curve that we ended up taking. It's not going to be the same as the domain for secant. The domain of secant involved all real numbers except pi halves plus pi k. We can't do that because we would have not a function. We would fail the vertical line test. The portion that we selected to make arc secant for y was from 0 to pi, but with an asymptote through the middle at pi halves. So our range, therefore, is 0 up to pi halves, with pi halves not inclusive, union with pi halves to pi, with again pi halves not inclusive. This is very similar to the range for arc cosine, which is from 0 to pi. Here we again have 0 to pi, but we have the point in the middle, pi halves, cut out. The symmetry is also going to share as it does for arc cosine. Arc cosine actually happened to not have any symmetry. It was neither odd nor even. That is also true for arc secant. It is neither odd nor even, which means if you have a negative input for secant, well, you can't really do anything with that. You cannot move the negative out to the outside or delete it or anything like that. So, gotta just use it as it is. In terms of the other information, it's going to be a repeat for the content from arc cosecant. If you take secant of arc secant, that will give you x so long as that input of arc secant actually defines a realistic triangle. For, in this case, hypotenuse over adjacent. For hypotenuse over adjacent, that has to be more than 1 or less than -1 technically. You cannot have anything between 1 and -1, as that would imply the hypotenuse is too small. When you apply secant to a function, or arc secant to a function of secant, that will cancel out and give you x so long as the angle measure inside of secant exists between 0 and pi halves, or pi halves and pi, aka as long as x, the value, exists within the range of arc secant. If it doesn't, we did an example like this for arc cosecant, but if you did arc secant of, let's say, secant of negative pi thirds, that is not just going to give you negative pi thirds. Instead, evaluate from the inside out. Secant of negative pi thirds will give you a positive 1/2. And then when you do arcsecant of positive 1/2, that will give you something within quadrant 1, where secant is defined to be positive. And specifically, this will actually give you pi thirds back in return. So be very careful when you're applying inverse functions to their trig functions. Lastly, just like with arc cosecant, if you do need to evaluate something like arcsecant of, I'll say, 10, that's kind of hard to approximate using a calculator, as most do not have arcsecant installed. Instead, we need to know how to change that into arccosine. Just like with arccosecant to arcsine, you're flipping the ratio, which in this case is the input for inverse functions. So this is equal to arccosine of the reciprocal of the input, 1/10. That is what the last line of these properties say. Arcsecant is the same as arccosine, but with the reciprocal of the input. Be very careful when you're trying to work with these functions and know how to change back and forth when you're applying reciprocal inverse functions.